So welcome to this week's Durham Geometry and Topology seminar. So it's a pleasure to have Tom Ducat, who just recently joined Durham as a Wilmore Fellow. And he will talk about the three-dimensional Lyness map and the Laurent phenomenon for OGr 510. Yeah, thanks, Tom.
So, yeah, thank you. So, yeah, I just joined Durham very recently, so I don't know. I don't think I've spoken to everyone here, but it would be nice to meet some of you more in person when we can, hopefully next year at some point. So I am algebraic geometer, and I know that the seminar here is not really, it's kind of a broadly speaking, a geometry seminar in a very broad definition. So hopefully I won't say anything too difficult or technical, but I just wanted to give you a kind of very overview of something that I think is very pretty, and that is to do with the geometry of this map called the three-dimensional Lyness map, and how it's related to a homogeneous space, which is the orthogonal Grassmannian OGr 510. So I'll try and explain what the orthogonal Grassmannian is and everything like that. So don't be put off by the words in the title, and hopefully this is just nice kind of playing around with equations and geometry of algebraic varieties. So here we go. So firstly, let me explain to you what the Lyness map is. So the Lyness map is a birational map of affine space. So it's just the map that's defined in terms of d coordinates, and it just shifts all of the coordinates to the left one, and then the last coordinate becomes the sum of 1 plus x2 plus x up to xd divided by the first one, x1. So it's a very kind of simple map, and obviously it's invertible because to do the inverse thing, I just have to shift back the variables in the opposite direction, and then I can recover x1 from the last term just by from that term. And so if I iterate this map and do it many times, either forwards or backwards by running the inverse of this map, then I can define a sequence of rational functions, and it's just defined by this recurrence relation, which is exactly the thing that tells you how to define the last term in the next term in the sequence, right? So for all I, so I'm given x1 up to xd to begin with, and then I can generate new elements in this sequence by this following recurrence relation, which is called the d-dimensional Lyness recurrence relation. And so this recurrence relation, when d is 2, is very famous. It's and it has a very surprising property, which is that it's 5 periodic. So if you start doing this map, so I start with x1 and x2, and then x3 is given by 1 plus x2, and then I divide by x1. And then x4 will be given by 1 plus x3, and I divide by x2. But when I write that in terms of x1 and x2, I get this thing. And then a very surprising thing happens in the next step, is that if I do 1 plus x4 and divided by x3, then when I write that in terms of x1 and x2, it actually looks a lot simpler than the last term. And then if I do it one more time, I find that x6 is equal to x1. So it has this very nice periodicity that is a priori completely unclear that you'll get that. And the same thing happens when d is 3. This recurrence relation actually is 8 periodic. So it's the period of the sequence increases a bit, but you still get this very nice periodic sequence, and these are the terms in the sequence here. And also for these two, when d is 2 or 3, notice that these sequences have something called a Laurent phenomenon, which is that all of these terms, so x1 up to x5 or x1 up to x8 in the d equals 3 case, are all Laurent polynomials in the first 3 variables or first d variables, which means that the denominator is always a monomial. And that's completely unclear that that will happen, because when I calculate the next term in the sequence, suppose I'm in the d equals 3 sequence and I want to calculate x8, then I have to form some polynomial in terms of x1, x5, and x6, and then I have to divide by x4, and x4 has a non-trivial numerator. So when I do that division, that has to divide the numerator of the sum, and that just happens by magic in this case. And so so you might think now, okay, that's d is 2 and d is 3, and what happens when d is 4 or more? And unfortunately, the sequence is crazy for higher d's. So it's not periodic anymore, and it doesn't have this nice Laurent phenomenon. So all of this nice properties of these sequences breaks down as soon as you go beyond the d equals 4 case. And so I don't really know much about integrable systems, but apparently, well, not apparently, when d is less than or equal to 3, iterating this map is an example of an integrable system, because this recurrence relation, so it has the maximum allowed number of invariant functions. So clearly, because these sequences are periodic, 5 periodic and 8 periodic, if I sum all the variables, or if I multiply all the variables and I apply the map to it, then that thing is going to be an invariant for the map, because it just shifts all of the things around one, and the periodicity helps you find invariant functions that way. But in general, because it's not periodic, when d is bigger than 4, this recurrence relation is not periodic, it doesn't have a Laurent phenomenon, and it's not an integrable system anymore. But it does still have quite a lot of invariant functions. So you can find a system of d plus 2 over 2, d plus 1 over 2 Laurent polynomials. So maybe some of the stuff that I explain in this talk can be made to work in those cases. But anyway, I'm going to focus on so the d equals 2 case is classical, and the d equals 3 case is what I'm going to hopefully explain in this talk. So what happens when the dimension of this in the d equals 2 case, so this 5 periodic sequence, so that 5 periodicity is really related to the geometry of a special surface, which is the del Pezzo surface of degree 5. And so let me explain how you go from that recurrence relation to the del Pezzo surface. So we have these 5 terms, which are the 5 terms in this recurrence relation. And this is known, I think, quite classically, that these are coordinates on a del Pezzo surface. So the del Pezzo surface is, I just take the ring generated by these 5 variables. And so these 5 variables satisfy equations such as x1 times x3 is 1 plus x2, and x2 times x4 is 1 plus x3, and x3 times x5 is 1 plus x4, and so on. So there's 5 obvious equations there. And those things cut out a surface in a 5-dimensional space. And that surface, which I'm calling U here, is this del Pezzo surface of degree 5. So if I take the projective closure of this surface, then I get a smooth, compact algebraic surface, which is the closed del Pezzo surface. And if I take the projective closure of this thing, then I have to add in some stuff at infinity, and it turns out that the thing that I'm adding in at infinity is a pentagon of rational curves. So these are 5 lines that form the boundary of a pentagon. And so the affine surface is just the projective surface y minus this pentagon of lines. So the pentagon of lines I'm calling D, and it's got 5 components. And so this surface U, so as it's well known that a del Pezzo surface contains 10 lines, and so any del Pezzo surface, or a del Pezzo of degree 5, contains exactly 10 lines when it's anticanonically embedded. And so 5 of the lines are forming this pentagon at infinity, and there are 5 more lines, and those 5 more lines lie in the interior of the del Pezzo surface, so they live inside this locus U. And there's a very pretty and beautiful configuration of lines here. So the 10 lines in this del Pezzo surface, 5 of them form a pentagon at infinity, and 5 of them form another pentagon in the interior of this surface, U, which is more like a pentagram. So every line meets the 1, 2 round to the top. And if you look at the dual intersection graph of these 10 lines, then you find that these 10 lines form a Peterson graph, or the dual intersection graph. So the dual intersection graph, for every line I draw a vertex, and for every intersection I draw a line, and then you'll find that these lines are dual to the Peterson graph. Very famous and beautiful symmetric graph. And actually, so we also know a del Pezzo surface of degree 5 you can obtain by blowing up 4 points in the plane in P2. And so this picture on the right shows you how to do that. So if I blow up these 5 points and look at the strict transform of all these lines, then I get this configuration on the left. And so the 5 periodicity of the sequence is really just the symmetry of order 5 of this surface, that just rotating this surface. And so the thing that sends x1, x2 to x2, x3, that's just rewriting this, all of the variables in this surface by doing a kind of rotation of order 5. And I want to make 2 observations about this example that are going to generalize to the dimension 3 case. So firstly, this U is something what's known as a cluster variety. So this is actually the simplest non-trivial example of a cluster variety. And I'll explain a bit about what I mean by that in a minute. It's usually the first thing that you encounter when you look at cluster algebras, and it comes from this A1, A2 quiver. And also, not only is it a cluster variety, but somehow it's related to this Grassmannian Gr25. Actually, it's a special hyperplane section of a Grassmannian Gr25 in a way that I'll also explain. And these are 2 things that I want to generalize in the d=3 case. So this variety U is a cluster variety. So what I mean by that as an algebraic geometer is probably quite different to what some of the other people in the audience think of. But for me, this is the interior, this in fancy language, this is an interior of a log Calabi-Yau pair. So log Calabi-Yau means that Y has a volume form, holomorphic volume form, which has a simple pole along the boundary D, and is non-vanishing on the complement, which was this affine space U, affine variety U. And this variety Y, projective variety Y with a boundary divisor D, has to have a toric model, which means that I can find a projective birational map that sends Y and D onto a toric surface Y bar and its toric boundary divisor Y D bar, where the map is an isomorphism from D to D bar. And so in our example, with the del Pezzo surface, I can blow down 2 of the disjoint -1 curves inside the 2 lines, I can contract 2 of the lines in the interior of U to get a map to a toric surface. So here is my Y is the del Pezzo at the top of this diagram here. And if I contract 1 -1 curve, then I get this surface here, which has 6 lines in it now, because it's got, it's got an intersection 0 curve and 4 -1 curves. And I can contract one of those 2 lines in the interior of U. And of course, because there's 2, I can do it in one of 2 different ways. And so for any pair of disjoint lines in the interior of U, I can contract them to get a toric variety. And for each line, I have exactly 2 disjoint, 2 other lines that are disjoint from it. So there's 2 ways in which I can do it. And if I change from one to the other, that corresponds to applying this Lyness map sigma. And so for me, if you're more familiar with the theory of seeds and mutations in cluster algebras, really I'm thinking here as the divisors inside this cluster variety, the things that are being contracted when I go to this toric variety, they are the elements forming my seed, and the mutation is the map that takes one of them and replaces it with another. And so the induced map that I get on toric varieties is actually exactly this Lyness map, which is the thing I started with. So that was U as a cluster variety. And now let me tell you what the connection with the Grassmannian is. So we can write the equations of this del Pezzo surface in terms of Pfaffians of a skew-symmetric matrix. And so the Pfaffian of a anti-symmetric matrix is, if the dimension is, well, it's essentially the square root of the determinant in some way. And there's a way to calculate those, just similar formula that you have for the determinant. And so this is a 5 by 5 skew symmetric matrix. So obviously its determinant will be 0. But if I look at any of the principal 4 by 4 minors, then I get, so there are 5 principal minors, and each of those has a Pfaffian, and those 5 Pfaffian equations are exactly the equations that define the surface. And so I have a matrix here, and the Pfaffians of this matrix define my surface. And of course I could homogenize this matrix quite nicely. So I choose to homogenize it in some special way. And this homogenizes the recurrence relation. So if I choose that, I can choose the indices of my yi's nicely so that I get this kind of homogeneous recurrence relation down the bottom here. And the point is that the resulting variety, the thing that's defined by these 5 homogeneous equations, well, because they're homogeneous, I could think of it as a projective variety, but also I could just think of it as the affine cone over that variety. And that's exactly, the thing I get here is exactly the Grassmannian Gr25. So by homogenizing this recurrence relation nicely, I get the Grassmannian Gr25, which is, you can just take to be the variety defined by these 5 equations, where the indices are supposed to be taken Z mod 5. So there are 10 variables here, x1 up to x5 and y1 up to y5, and they satisfy these 5 equations. And so if I project this affine cone over the Grassmannian onto the affine plane that's spanned by those 5 homogenizing variables. So you can think of them as frozen coefficients in the cluster algebra, if you know what that is. And so I get a family now of del Pezzo surfaces. And so for the general fiber of this fibration of del Pezzo surfaces is the thing I started with, but actually if some of the variables that I added in, the yi's, are allowed to vanish, then these things start to degenerate, and I get this family of del Pezzo surfaces that are degenerating over the coordinate strata of this affine space. And the worst fiber in the middle here is just the cycle of 5 coordinate planes. So I'll see something similar in the dimension 3 case. So I just want to bring that up, but this is kind of related to the theory of toric degenerations of this surface U. And anyway, let me move on and talk about the dimension 3 case. So in dimension 3, there's another very famous algebraic variety here. So before we had a del Pezzo surface, and in dimension 3, the main player is going to be this Fano threefold called the Fano threefold V12. And I'll explain a bit about that in a minute. But let's just recall that we have these 8 functions, which were the 8 functions that come from the 8 periodic Lyness recurrence relation. So those 8 functions generate a ring. 8 rational functions generate a ring, and that ring is the coordinate ring of a threefold. If you calculate the dimension of that, you expect to find something 3-dimensional. embedded in an 8-dimensional space. And so the question then is what's the geometry of this space? And obviously, can we do all the nice things we found out about the 5 periodic relation and the geometry of the del Pezzo surface? Can we repeat that in this case? And so just as the affine del Pezzo surface was a kind of dehomogenized version of this Grassmannian GR25, it turns out that there is another kind of Grassmannian which is lurking in the background here, and that's precisely the Grassmannian I mentioned in the title of my talk. So I actually wrote OGr 510, but the orthogonal Grassmannian OGr 49 is isomorphic to it. So there's a reason for that, why I've changed notation that I'll say in a minute. But this orthogonal Grassmannian, so it's like a Grassmannian. It parameterizes planes in an affine space, but in this case, the space that I'm parameterizing the planes in has to have a quadratic form, and the planes that I'm parameterizing, I want them to be isotropic with respect to that quadratic form. So that's what this thing is as a homogeneous space, or as a Grassmannian rather. And as I said, the OGr 510 is actually reducible. It has 2 components, and each of those components is isomorphic to this OGr 49. So it's a homogeneous space, as I said, and for OGr 49, the relevant Lie group here is the Lie group SO9, which is of Lie type B4. And this OGr SO9 has a representation called the spin representation, which is the 16-dimensional representation given here. And the weights of this representation span a polytope in the weight lattice of this group. And actually this polytope is very simple. It's just a 4-dimensional hypercube. And the hypercube has just the vertices plus minus a half. So there's 16 different vertices here. And of course, if you look in 4-dimensional real space, at the locus defined by these 16 points, it's just a hypercube. And the veil group of B4 is just the symmetry group of this cube. And there's this very special symmetry that this hypercube has, which is called the Coxeter rotation, which is just the composition of all simple reflections in B4. And that just as a symmetry of this cube, it's a rotation of order 8. And this is very nice because you can then project this thing onto a plane called the Coxeter plane. And this is now a projection of a 4-dimensional hypercube, and it has a very obvious symmetry of order 8, which is just a rotation. So for instance, you can see lots of cubes in here in this picture. We'll see a cube in a minute, but there are lots of 3 cubes in this picture, and actually taken all together, this thing is a hypercube of dimension 4. And so in order to define this orthogonal Grassmannian, this homogeneous space, for every coordinate, every vertex of this cube, I need to introduce a new variable. And so I'm going to label all of the variables x1 up to x8 and y1 up to y8 according to the vertices that I have in this cube in the given way. So the numbering, as I rotate around by 1, the number jumps by 3. So it goes 1, 4, 7, 2, 5, 8, 3, 6, 1. And x1 is opposite y1, and x2 is opposite y2 in this picture. So they're antipodal vertices in this cube. And so they're the generators of the coordinates, the distinguished coordinates on this Grassmannian. And the way that you read off the equations for this Grassmannian is that you look at the cube faces, the 3 cube faces of this hypercube, and the way that this thing has been projected, 2 of the variables appear in the middle here, so x1 and x4, and then I multiply those 2 things together, and then that thing is equal to the I work around the vertices outside the cube and I multiply together antipodal points and I add them together. So this red cube that I've drawn here, this corresponds to an equation, which is x1, x4 is equal to y2, x2, y5 plus x3, y8 plus y2, y3, which is just the given by looking at antipodal points in this cube. And so the 8-fold symmetry now gives you 8 more equations, just exactly the same as this. So this equation is periodic mod 8 if I rotate the coordinates, if I spin the cube around. And there are 2 more equations, so there are 8 equations like that. And if you look at the ideal defined by those 8 equations, it actually implies 2 more equations, and those are some equations of the form x1 times x5 minus x3 times x7 is y1, y5 minus y3, y7. But these are just some 2 extra equations that you get given for free when you have those 8 equations, and they're actually important for a reason we'll see in a minute. And so let me just summarize. If you're completely lost, let me just summarize what I've done for you. We've got an affine variety here in a 16-dimensional space. So the coordinates are xi and yi, and it is defined by these very nice 8 periodic symmetric equations. So x1, x4 is blah, 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 dot, dot, dot. And then these 2 additional equations at the bottom here, x1, x5 minus x3, x7 is y1, y5 minus y3, y7, and so on. And so really, if you want, and to be honest, this is more or less where I started this project, you can just assume that you start with the variety that's defined by these equations here. And so, what's nice about these equations is that you know that if I set the yi's all equal to 1, then I precisely get the Lyness recurrence relation back for the for d equals 3. So here, if I'm ignoring all of the yi variables, I've got the equation x1, x4 is x2 plus x3 plus 1, which was precisely my Lyness recurrence. And this 8 periodicity now is the 8-period cyclic rotation of this orthogonal Grassmannian that you find. This is as I just said, this is a very nice homogenization of the 3-dimensional Lyness recurrence. And so I have this variety that's defined in terms of these 16 variables, and if I project to the 8-dimensional plane that's spanned by the yi's like I did before, then I get a flat family of affine Fano 3-folds. So the general fiber here is an affine Fano 3-fold, and it's a Fano 3-fold of that's known classically. It's called the V12, and this V12 is exactly defined to be the intersection of the Grassmannian OGr 49 with the hyperplane section of the codimension 7 of codimension 5. Sorry, so dimension 7. But what's very interesting about these in this case is that these affine Fano 3-folds, when you take the projective closure of them, you get something that's very singular. And so that's a little bit surprising, but or was to me when I first did it, but it turns out to be crucial in terms of the geometry of what's happening. And so if I look at the fibers of this map pi, so you can think of just this as fixing some choice of frozen variables in some kind of cluster algebra. So the fiber of this map, there are 2 conics in the base of this fibration given by these 2 equations here. And above these points, all of the fibers of this map pi are isomorphic. So essentially there's a 2-parameter family of fibers here that are parameterized by these numbers lambda and mu, which are the ones given here. And if I take the projective closure of this, I get this Fano 3-fold, which is got 16 singularities. So I think this is like the limit, the most number of singularities that a Fano can have of this type without having to have curves of singularities and things like that. So so it has these 16, so the boundary divisor at infinity has 10 components to it. And the 10 components are 8 copies of the projective plane P2 and 2 copies of the P1 cross P1, that's these 2 squares. And they meet in this configuration, this very nice configuration of a polytope that obviously has an 8-fold symmetry. And these nodes are placed at the corners. So these singular points of this compactification are placed at the corners and along these 8 edges that go around the outside here. And so I told you, so we knew, so in the 5-dimensional case, you can obtain the del Pezzo surface by blowing up a toric variety. And in this case, we can also obtain this 3-fold by blowing up a toric variety, a very simple toric variety, just the affine 3 space. And so before we had to blow up 2 points, 1 on each coordinate axis. But in this case, we have to blow up 3 lines in this space in order to get this 3-fold u lambda mu. And so these are the lines. So there are 2 lines, one in the hyperplane x1 equals 0, one in the hyperplane x3 equals 0, and we have to blow up a conic that lives in the hyperplane x2 equals 0 in order to understand what this variety u is. So there are basically 4 cases that we can have for a fiber of this fibration. So if the general case is this case 1 on the left here, so I've drawn here, so the dotted lines here are the coordinate axes in A3, and we can think that the hyperplanes are the planes that go between these 2 coordinate axes. And so in general, in order to realize one of these fibers u lambda mu, I have to blow up 2 lines and a conic, and they meet in the configuration that's given in this one on the left here. And if one of my parameters becomes 1, then this conic degenerates, but otherwise it's irreducible. But for certain values of mu, so when mu is 1, this conic splits into a disjoint union of 2 lines. And when lambda is 1, the 2 lines on the top here, which were disjoint, they actually touch, and you get a little embedded point in the intersection there that you also have to blow up if you want to understand what this projection does. And if lambda and mu is equal to 1, then that's the most degenerate case. You get this picture on the right here. So in general, a fiber you get by blowing up 2 lines and a conic. But when one of these parameters becomes 1, I have to blow up 4 lines, the 4 lines given here. Here, case 3, I have to blow up 2 lines, a conic, and a point, the point that meets in those 2 lines. And then in the worst case, case 4, I have to blow up a point and 4 lines, the 4 lines drawn in the picture. So, so let's just consider the generic case, this case 1 here. And let me explain to you what the mutations are in this picture. So when I blow up these 2 lines and a conic, I get these 3 exceptional divisors, and they're the exceptional divisors that get contracted when I consider the projection u to A3. And these divisors get contracted to the line L1, the conic C2, and the line L3 respectively. And so the mutation will be to blow up the L1. For example, if I want to mutate E1, I have to blow up L1 and then contract the strict transform of the divisor above it. And so that corresponds to just doing this, Lyness map at the coordinate x1. So if you understand what that does in the geometry, it blows up this line and then it contracts the divisor above that line. And so that's what happens when I mutate E1. And similarly, when I mutate E3, I'm doing the inverse of the Lyness map. And so then there's this question about what happens if I try and mutate this divisor in the middle. So that corresponds to blowing up the conic and then contracting something above the conic. And so that in coordinates is given by this map here. And so the numerator of this term here is exactly the term, you see it's a conic in x, so x1, x3, plus something linear in x1 and x3 and a constant. So this is the equation that defines the conic that gets blown up. And so if I throw this in, if I define now a new variable, q1, which is going to be the ratio of this thing here, this new variable turns out to have even though it looks very complicated here, actually, if I were to write it in terms of the other variables, it has a very simple expression in terms of x1, x3, y1, yeah, in terms of the other things. So it's just exactly this term here. In fact, it's a regular function in terms of x1, x3, and the other things. And so if I also similarly, if I add in a q2, which is given by the rotation of q1, then I get a system now of 10 coordinates in this cluster threefold, and so I get this nice system of torus charts. So it turns out that this system of cluster variables is closed under mutation. So what I have here is each point in this, each vertex in this polytope is corresponding to a toric model of my original cluster variety, so a blow down to a toric variety. And each of these edges is corresponding to one of these mutations, which is thought of as a kind of blow up, blow down operation. And this system of torus charts and mutations is closed. So I can go around in any order and I'll get back to where I say I will if I follow a loop on the boundary of this polytope. And so this also holds in the other cases where I have some degenerate behavior. So if one of those variables was allowed to become 1, then the centers in which I blow up start to degenerate, and then I can actually blow up in more than 3 different ways. So I can blow up lines. So in this case, case 2, well, in case 1, I have to, if I want to mutate this conic, I have to blow it up. But in case 2, the conic splits into 2 components. So then I can blow up one of the components, but not the other, or I can do vice versa, or I could blow them both up. So in these degenerate cases, you get more directions in which to mutate, and you get exchange graphs that look like 4-dimensional and 5-dimensional polytopes, respectively, and they're much more complicated, but they are also actually finite in this case. So, so there's some kind of enhancement that you can make to this exchange polytope. But let me just explain. I just want to do a few. I said in the abstract that I would like to try and explain a little bit about why I'm interested in this space and what it has to do with applications to mirror symmetry. And so I don't really want to have to explain a lot about mirror symmetry, but I'll just try and give you a flavor of why this variety U is very interesting to me. And so I'll just give you kind of brief application to mirror symmetry and the kind of amazing geometry really that this thing has. Let me consider either the affine del Pezzo surface or the affine Fano threefold V12 that I've defined in this talk. So these are the 2 varieties defined by the Lyness recurrence in dimension 2 and dimension 3. Then really this cluster algebra structure is controlled by something called a scattering diagram. And what the scattering diagram is I draw a fan. So the case for the del Pezzo surface is on the left here. I draw this fan, and this fan is actually the fan of a toric variety, because the toric varieties are defined by fans, and the toric variety is actually the toric model in this case of the cluster surface. So both of these cases, the case d equals 3, you get this much more complicated looking three-dimensional fan. But you notice that for every point, every ray in this fan, I have an associated cluster variable. And if I move through walls in the chambers, if I move between chambers in this fan through walls, then that corresponds to doing mutations. So these fans are actually dual to the exchange polytopes of the cluster varieties. And so not only is this thing a fan, well, because this thing is a fan, these points, you know, there's an underlying space here, which is either R2 or R3, and that R2 and R3, it has an underlying lattice, an integral lattice, right? And the fan, of course, has to play nicely with the integral structure. These points are, these lines have to be rational, for instance, and the cones are all rational. In fact, the cones are all smooth in terms of toric geometry. And so the lattice points now of this space, because I have this fan structure and I have the cluster variables living on certain rays in these cones, I can associate a basis of monomials to the integral lattice points in this space. And so, for example, in each of these cones, if I look at the lattice point here, that it lies between x1 and x5, that corresponds to the monomial x1 times x5. And the second lattice point on array is going to be, so here I have point x5, and the second lattice point along is going to be x5 squared. So I can associate a monomial to each lattice point here just by looking at the generators of the cone it lives in. And I can do the same thing over here in this more complicated example, and I get a distinguished basis. This is, if you've heard of the Gauss-Seibert program, these are theta functions on the variety U, and this is the lattice of theta functions. And if you notice, the fan is dual to the polytope that was given the divisors. So in the case of the Del Pezzo surface, the divisors infinity formed a pentagon. And the case of the affine V12, I had 10 divisors in the boundary, and they formed this polytope here, which had 8 copies of P2 and 2 copies of P1 cross P1. And the number of divisors in the boundary there is equal to the number of cluster variables I have in my cluster variable, in my cluster algebra. And that's not, it's more than just a coincidence. Because the fan is dual to the polytope that I've drawn here, I can think of these lattice points either as monomials on my variety, or I can think of them as divisors in compactification of my variety. And this is something to do with the fact that these things are self-mirror in some special way. And so I have this space, which just it just looks like the real, Rn. With an integral structure and this fan in it. And because these points have 2 interpretations, one is as a boundary, one is as a monomial, I can think of it as a monomial, just a regular function, special type of regular function on my variety. And then another interpretation, I can think of a point in this lattice as being a boundary divisor in a compactification of my variety. And so because I've got those 2 points of view, I can write down an intersection pairing on this space, which is just given by computing the order of vanishing, and so of a monomial along a divisor, like you do in toric geometry. And so this intersection pairing, of course, it depends what cone you're in order to compute it. But it turns out that this intersection pairing gives this space B, which is, it looks like a real Rn, but it has this funny intersection pairing on it, which gives it the structure of an integral affine manifold with singularities. So the intersection pairing gives you a way to define an affine structure in this space, but the affine structure doesn't extend to the whole space. And what actually happens is that some lines are forced to bend as they pass through walls in the scattering diagram. So this is the 2-dimensional case. On the right-hand side here, I have the lattice, and I'm thinking of the points as monomials on my del Pezzo surface. And here I have the monomial 1 plus x plus y over xy, and it lives at this point on this ray along here. That was one of the 5 terms in my recurrence relation. And if I look at all of the, if I now take the same lattice, but I think of all of the points as divisors in a compactification of U, and I look at the order of vanishing of this thing along these divisors, then the locus of divisors which has a pole on is this bending line here. So this line that bends around the back of the origin here. This is the set of all divisors along which this monomial has a pole. And so you can see that it's forced to bend when it crosses rays in the scattering diagram. And that corresponds to the fact that really the variety that I had here was given by the toric variety defined by this fan, except I had to blow up 2 points, and the 2 points were the 1 point along each of the boundary divisors that these 2 rays correspond to. And so even though you have this affine manifold with singularities, it's like a non-flat. You just think that this space is not flat, it's kind of bent, and it bends. So lines have to bend as they pass through these 2 rays. But so it doesn't make sense to talk about the linear structure at the origin here, because if a line comes around this way, it has to bend. Of course, if a line went from this point to this point in a straight line, it wouldn't have to bend. And if you kind of shrink the 2 points down to the origin, then of course you can't make sense of lines that pass through the origin, because either side of the origin, they go off in different directions. But the nice thing in this case is that all of the tools of toric geometry generalize to this setting of integral affine manifolds. So I've got 2 dual lattices here, one which is points parameterizing monomials and one where points parameterize divisors. And basically that's the setting of toric geometry, where the center of your interior of your space is a toric variety. Here it's a cluster variety, and these 2 spaces are basically playing the role of the lattice, the 2 different lattices that you have in toric geometry. And because you have these 2 lattices, and you have a way of dualizing between lattices, so just like you have in toric geometry, a polytope in one space corresponds to a compactification of the torus. And in this case, a rational polytope drawn in this lattice corresponds to a compactification of our cluster variety U. And because the lines are allowed to bend, you can get some exotic kind of polytopes that you wouldn't normally find in real life. Like, for example, in the picture here, this is a bigon, so it's a polygon with 2 vertices and 2 edges. So the edges here are actually straight lines, but they're straight lines in the affine structure. So the fact that they bend at the points here is just to do with the fact that they're actually secretly straight. It's just that we can't draw the affine manifold B in a flat plane. And so, because you have a dual intersection pairing between these 2 spaces, where it's really just the same space, you can dualize polygons in the way that you would do normally with respect to the affine structure. And so here are 2 dual bigons. So again, this one is also a bigon. So the line that goes around the outside here is actually straight, because they're forced to bend along these 2 lines. So it has exactly 2 vertices, the one at the top left and the one at the bottom right here. And so these are 2 dual polygons, and they correspond to 2 dual compactifications of the same cluster variety U. And this is just a version of mirror symmetry between 2 compactifications of this variety U, in the same way that Batarev duality between reflexive polytopes in normal space is a form of mirror symmetry between toric Fano varieties. So sorry, I don't really have much more to say about that, but essentially that's kind of why these spaces are interesting, because you can play all of this kind of toric geometry game with them, and they're actually, amazingly, in this case, these lattices are self-dual in the sense that the intersection pairing between the lattice. It has an intersection pairing with itself. Normally, in higher dimensions, you wouldn't expect mirror symmetry to be you'd expect the lattices to be different, but in this case, they are the same. So it's a very special property of these two examples, I think. Anyway, that's the end of the talk. So I'm happy to take any questions, but yeah, thank you.